Now we go to saddle points and extreme values. In order for us to find the local minimum and local maximum using partial derivatives, it means, firstly, the point that we're talking about, point 8b, must be at an interior in that particular domain, and both derivatives with respect to x and with respect to y must exist. So this derivative have to exist as because we're going to find the first derivative with respect to x at that particular point and equate it to 0, because we know the first derivative test requires that the first derivative be equal to 0 at the stationary point. So hence it works even here. First derivative with respect to x and first derivative with respect to y. Both of them equated to 0. That means that particular point will have then to be determined whether it's a local maximum or a local minimum. So all in all, if you've got a particular point in the domain, the first derivatives exist, and you discover that the first derivatives, both of them with respect to x and with respect to y, at that point are equal to 0, then you know that that particular point is either a local minimum or a local maximum. Now, how then do you determine which one is maximum and which one is minimum? Number 2 is talking about the nature now of the stationary points. How do we determine whether a particular stationary point, now that you know it's a local max, it's either a local minimum or local maximum, how do you determine whether it is a critical point, which is a minimum, critical point, which is a maximum, which is a saddle point, or actually the problem or that particular point does not give you any conclusive result? What we do is to calculate. It's either you use fxx times fyy minus the mixed derivatives squared, or you use the determinant, making sure that the first row is fxx, fxy, and the second row fyx and fyy. Remember, fxy and fyx are equal according to Clairaut's theorem at that particular point. So now we call that determinant D. So we use D as well as the nature of fxx, that is the second derivative with respect to x, to check whether we're having a minimum or a maximum or a saddle point. We need to use those two. So if you get D to be positive and fxx also positive, then that means your stationary point is a minimum, local minimum stationary point, critical point, extreme local extremum or local minimum, local. So because there are many ways, or local turning point, there are many ways that we are using, or many terms that we're using, but for now let's stick to local minimum or critical point or stationary point. So once again, if D, which is the determinant of that matrix, if it's positive, and fxx, that is the second derivative, is also positive, that means that stationary point is a minimum. Then how should it be for a maximum. We go to B. If you get, again, note that D must be positive, but the second derivative with respect to x is negative, then you get a local maximum. So local minimum and local maximum, both of them, that determinant D must be positive. For minimum, fxx will be negative. For maximum, fxx will be negative. Then we go, what happens when D is not positive now? It is negative. Then we say we've got a saddle point. But then after doing your finding that determinant, we get the result that D is equal to 0. Then we are going to say the results are inconclusive. So we'll have to find or figure out ways to make sure that we know exactly what is going on at that particular point. Because definitely, if D is equal to 0, it does not give us any idea whether it's a maximum or a minimum or a saddle point. Let's do some examples so that we can be able to figure out how or which results will give us a local maximum, local minimum, and saddle points and inconclusive result. We are told here to find the local extreme values. We know local extreme values, it means local minimum, local maximum, saddle points, and also inconclusive results. We've got x squared plus y squared as our function. So we know we have to find those derivatives. First derivative with respect to x and first derivative with respect to y, and also the mixed derivative fxy and fyx. And then find the second derivatives fxx and fyy. I'm hoping you are checking my results. And then the next thing, find D and substitute. Remember, the first term is fxx times fyy minus fxy all squared. So now substitute fxx, we got 2, fyy, we got 2, and both our mixed derivatives gave us 0. So our answer is 4, and we know 4 is positive. But then we go back. If D is positive, we need to check the second derivative with respect to x. Was it also positive? Yes, we got a positive result. So that means the critical point is a minimum. But then what is the critical point? Because we need to find the critical point. Remember, in order for you to find the critical point, which is also the stationary point, what do? First derivatives, both of them must be equated to 0, and you solve for x and y. Please remember this. Stationary points, turning points, critical points, you all find them using the first derivatives. First derivatives, both derivatives must be equated to 0, and you solve. And then you'll be able to say your critical point or your turning point or your stationary point is 0, 0 according to this problem. Let's go to the second one. You've got y squared minus x squared. We also do the same. Find the first derivatives, both of them, and also find the mixed derivatives, both of them. I'm hoping you are checking whether my results are correct. Then find the second derivatives and then thereafter substitute into d fxx times fyy minus this mixed derivatives squared. We got here -4, which is less than 0. Immediately we get a less than 0. We know we've got a saddle point. Remember, for minimum and maximum, D must be positive. But if D is negative, then that means we've got a saddle point. Again, here the critical point, we have to find it using the first derivatives, and then we got a 0, 0. Number 3, we've got now xy minus x squared minus y squared minus 2x minus 2y plus 4. Same story. First derivatives, mixed derivatives also. Please check whether my differentiation is correct. And then we go to the second derivatives, and then we go to the formula, D. In this case, we got D to be positive. Immediately D is positive. Then we go back and check how was our fxx. And here we got negative. So if D is positive and fxx is negative, then we've got a maximum critical point. And then find the critical point. First derivatives equated to 0, and then solve. Now note, here my first derivatives, y minus 2x minus 2 equal to 0. And the second one is x minus 2y minus 2 equal to 0. We use simultaneous equations to solve, and please check if you are going to get the same solution, that the critical point is -2, 2. Here are some exercises. Please make sure that you check your differentiation. Remember that for these problems, we can give you any kind of an equation as long as it's got mixed variables. It could be hyperbolic functions, inverse hyperbolic functions, inverse trig functions, could be in there. Anything could be in there. So please be able to remember your differentiation rules, all of them. It could be composite functions that will require you to use the chain rule. Make sure that you've got everything right. Then we go to total differentials, or what we call the small change. The estimated small change, what we call the small change, to move from a point x0, y0 to a point x0 plus dx, y0 plus dx, which is just nearby, is given by the formula df. And I need you to remember, it's an estimate. Hence, we do not use an equal sign, we use an approximation sign. So it is very important not to use an equal sign for the small change problems. So df is approximately equal to fx at that point multiplied by dx plus fy at that point multiplied by dy. This could be rewritten as delta. D can just be changed to delta. So you'll find in other textbooks and in other notes, they are not using dx, df, or dy. They are using delta f, delta x, and delta y, just to give a difference between the derivatives and the small changes. So most of the time, you'll discover that most textbooks use the second formula. And this is what is called the total differential of f. So I need you to note that the first term is fx at the given point multiplied by that small change, which is delta x, fy at that particular point multiplied by the small change. This gives us the small change, which is the total differential of f, and it is an estimate. That is why you see that term, the estimated small change. Don't use equal signs. Please use the approximation sign. Let's do some examples. Here we have an estimated change in volume as our number one. Suppose that we have firstly the shape, cylindrical can. So immediately have cylindrical, then we need to know, is it surface area, volume, what are the formulas? And it has been designed. Firstly, the radius is given to be 1 inch, and the height of this cylindrical can is 5 inches. But the radius and height are off. Let us say you were designing this can, and then when you bring it in for evaluation, we do the measurements. We discover that you've messed up a bit. So your height and radius have been off. The small change, you added 0.03 to your radius, and your height is short by 0.1. So note the addition. That means you went off the mark, you added 0.03. That's why there is a plus there, and your height is less by 0.1, hence the negative. Now they are saying here, estimate the resulting absolute change in the volume, in the whole volume of the can. These errors in measurements, what have they done to the absolute, to the volume? What is the real resulting absolute change you've caused in the volume of the can by making those small errors in measurements? So the first thing we do here, we need to figure out the volume of the can, because that's what they are talking about. They are talking about a change in volume. So the volume of a cylindrical can is pi r squared h. Now we bring in the formula that we know. Now it's delta V is approximately equal to V. Note that our V has got two variables, R and H. We don't have X and Y now. So that means V will be differentiated with respect to R first. And note that this is the original, that those are the initial values. And then dr, which is the error. And then we've got V differentiated with respect to H, and then the error in height. Let's substitute. What is the derivative of V with respect to R? Note that pi and H will be constant, so you're differentiating R squared. You will have 2 pi RH multiplied by dr. We have not substituted anything yet, plus we are just differentiating V. So V differentiated with respect to H, so that means pi and R squared are just constants, so that means you'll have pi R squared times DH. And then we remember, what are the initial values that were given to us? R naught, the initial radius that we're supposed to use, is 1 inch. We write it as R naught is 1, H naught is 5. dr, we know it's positive 0.03. dH, we know is negative 0.1. And then we go to our derivative and do the substitution of all those values. Remember, that is why it's written here VR of R naught H naught. That means in your differentiation, in order for you to find the total differential, you substitute the initial values that were given multiplied by the error, which is the small changes. And then we substitute. We've got 2. And I'm hoping that you are noticing that whatever we do, we have dV on the left-hand side. And the approximation sign must always be there. 2 times our initial, R is 1, and then we've got pi. Then our initial H is 5, multiplied by dr, which is 0.03. And then we go to the second term, we've got pi, and R naught is 1, so we've got 1 squared, multiplied by dH, which is negative 0.1. And then you get your solution. Please remember that we have to have the units in there. R squared, each R is measured in inch. R squared will give you inch squared, and H is inch. Hence, we have inch cubed as our final unit for the total differential, or the absolute change in the volume of the can. Number 2, now we are looking at the applications to electrical circuits, or because here we've got the power that has been consumed by an electrical resistor, and the formula has been given. P is equal to E squared over R, and is measured in watts. E is 150 volts and R is 9 ohms. Question is, by how much does the power change if E decreases by 7 volts? So note it's decreasing, and R is decreased also by 0.3 ohms. Now we need to figure out delta E and delta R. Decreasing means negative, so that means delta E is -7 and delta R is -0.3. Now, first things first, let's put in the formula. Delta P is approximately equal to P differentiated with respect to E, because what you need to note, you just have to go back to the formula. What variables does it have? So you differentiate P with respect to E and P with respect to R, because those are the only 2 variables in that power formula. So, and note that we are going to substitute the initial values for E and R, multiplied by delta E, also the differentiation of P with respect to R, multiplied by delta R. So when you differentiate with R, you multiply by delta R. When you differentiate with respect to E, you multiply by delta E. The derivative of P, we go back with respect to E, it becomes 2E over R. Note what I've done here is just to substitute E naught and R naught, so that we understand that whatever we're going to get, will substitutions be based on the initial values of E and R multiplied by delta E, and then we go to the derivative of P with respect to R. Note R is in the denominator and E squared is just a constant. So it gives us negative 1 over R squared multiplied by E squared. So that's why we've got that expression for delta P. And then we do the substitution. The initial value that was given for E was 150, and the initial value that was given for R is 9, and the small change that happened is -7 for delta E. And then again, on the side of the derivative with respect to R, we do the substitutions again. We've got 150 squared divided by 9 squared multiplied by the change in R, which is negative 0.3. And then we get our approximate electricity that has been consumed by that resistor, or power that has been consumed by that resistor, to be negative 150 watts. Hence, then we say the power is reduced by approximately 150 watts. That is your final answer. Please make sure that you have that final conclusion in words, because it was a word problem. Here are some exercises for you to do. It's just a few of them. Please look up for other exercises that involve small changes. Number 3 is talking about the radius of a cylinder. Now you've got a cylinder, and because you've got a cylinder, you have to go to the question. We need the volume change. So what is the formula for the volume of a cylinder? You need to know. Also for number 4, we've got here an area of a right-angled triangle. You need to know the formula for the area and then make those changes. What is the change? Which one was increasing, which one was decreasing? So which one will be positive, which one will be negative? And the initial values, and then we get the approximate change. Then number 5 takes us back to the higher derivatives. Remember, we only did up to fxx and fyy and the mixed derivatives. So we're just on second order derivatives. Now takes you back to the third derivative. Please show that that function is a solution to that equation. In order for you to be able to show it, it means you substitute it into the equation. So you have to take the left-hand side first, substitute the given z, simplify, do the derivatives and simplify, and see what you get. And then thereafter, you take the right-hand side, you do the same. Substitute, simplify, and see what you get. If you get the left-hand side equal to the right-hand side, then you'll be able to say Z is a solution to the equation. But if your left-hand side is not equal to your right-hand side, then this equation that has been given to you is not a solution. Attempt it and let's see what you get. Please consult if you've got any questions.